We're using the method of undetermined coefficients to find one particular solution of a non-homogeneous differential equation. Then we're going to add that to all possible solutions of the corresponding homogeneous differential equation to get all possible solutions of the non-homogeneous differential equation. Let's look first at the case where that right-hand side function is a polynomial times an exponential. So we have a non-homogeneous differential equation, non-homogeneous because we've got a function f of x on the right-hand side, which is not 0, and the corresponding homogeneous differential equation is the same, where we replace f of x by 0. Now, if f of x equals some constant x to the k e to the ax, where a is not a root of the auxiliary equation, then we're going to set yp to be equal to a polynomial of degree k with coefficients that we don't know yet times that exponential function. So we're replacing this x to the k with a general polynomial degree k, and we might need these lower power terms. And then we plug yp and its derivatives into the non-homogeneous differential equation to solve for a0, a1 up to ak. Now, having a polynomial times exponential on the right-hand side has some special cases I want to point out. If a equals 0, then we have e to the 0, which is just 1. So f of x is just going to be constant times x to the k. And then in our particular solution, we don't need the exponential part, because that again will be e to the 0. So yp is just the polynomial part. On the other hand, if we have k equals 0, that means there's no x here and we just have exponential. So f of x equals just c e to the ax. And then y of p is going to be, if k is 0, we don't need any of this except the constant term. So we have a0 e to the little ax. And if k and a are both 0, that means that the right-hand side is, there's no exponential, there's no polynomial, we just have c, and then we'll let yp be just the constant a0. Now this all holds if the number a in the exponent is not a root of the auxiliary equation. If a in the exponential is a root of the auxiliary equation with multiplicity m, so that means that x minus a to the mth is a factor, then all we do is multiply this by x to the m before we take derivatives and solve for the coefficients. So multiply by x to the m, where m is the multiplicity. We do that before differentiating. All right, so let's do some examples. All right, let's look at the example. Let's let our non-homogeneous equation be y double prime plus 6y prime plus 9y equals 5e to the 2x. Then the homogeneous equation is y double prime plus 6y prime plus 9y equals 0. The auxiliary equation is r squared plus 6r plus 9 equals 0. That's r plus 3 squared equals 0. So r equals -3 is a double root. And our basis for the solution space of h is e to the -3x and x e to the -3x, because when we have a double root, the second time we multiply by x. All right, looking at the right-hand side, we don't have any polynomial there next to the exponential. We'll try yp equals some constant e to the 2x. So then the derivative is going to be 2a naught e to the 2x, and the second derivative is 4a naught e to the 2x. Then plugging these into the non-homogeneous differential equation, we have second derivative 4a naught e to the 2x plus 6 times the first derivative plus 6 times 2a naught e to the 2x plus 9 times the original function plus 9a naught e to the 2x equals 5e to the 2x. So that is, well, we can factor out e to the 2x on both sides. That leaves us with 4a naught plus 12a naught plus 9a naught equals 5e to the 2x. So this part, this is 16 plus 9, 25a naught equals 5. So that means that a naught is 1/5. So our particular solution is 1/5 e to the 2x. And all solutions to the non-homogeneous equation are 1/5 e to the 2x plus any multiple of e to the -3x plus any multiple x e to the -3x. So C1 and C2 are real numbers. So again, our solution to the non-homogeneous differential equation is one particular solution plus all possible solutions to the homogeneous system. One solution to non-homogeneous plus all possible solutions to the homogeneous equation. All right, let's look at another example. Let's let our non-homogeneous equation be y double prime plus 2y prime plus y equals 4x squared. So then our homogeneous differential equation is y double prime plus 2y prime plus y equals 0. The auxiliary equation is r squared plus 2r plus 1 equals 0. So that's r plus 1 squared, and r equals -1 is a double root. So all solutions to the homogeneous differential equation are any multiple of e to the negative x plus any multiple x e to the negative x. Now, because of the right-hand side, which is a polynomial with no exponential part, we can try particular solution equals constant plus constant x plus constant x squared. Then the derivative is a1 plus 2a2x, and the second derivative is just 2a2. Now if we plug this into the non-homogeneous differential equation, we have second derivative, so 2a2 plus 2 times the first derivative, a1 plus 2a2x, plus the original function, a0 plus a1x plus a2x squared equals 4x squared. And then we can solve for a0, a1, a2 by comparing coefficients of different powers of x. So on the left-hand side, our constant term is 2a2 plus 2a1 plus a0. On the right-hand side, our constant term is 0, because 4x squared is 0 plus 0x plus 4x squared. And then if we compare coefficients of x, on the left-hand side we have 4a2x, and then a1 plus a1. On the right-hand side there's no x's, so 0. And then if we look at coefficients of x squared on the left, we have a2x squared. On the right-hand side we have 4x squared. So we have these three equations. The last one tells us a2 equals 4. And then the second one tells us, well, 16 plus a1 equals 0. So I guess a1 is negative 16. And the first one tells us, let's see, 2a2. So that's 8 plus 2a1 minus 32 plus a0 equals 0. 32 minus 8 is 24. So this is negative 24 plus a0 equals 0. So that means that a0 equals 24. So that means our particular solution is 24 plus a1x, 24 minus 16x plus 4x squared. And all solutions to the non-homogeneous equation are 24 minus 16x plus 4x squared plus any multiple e to the negative x plus any multiple x e to the negative x. So this comes from the homogeneous differential equation, and this is yp. Alright, now let's do an example where we have an exponential on the right-hand side that has a coefficient of x in the exponential that comes from the characteristic equation, the auxiliary equation. So let's let our non-homogeneous differential equation be y double prime plus 2y prime plus y equals e to the negative x. The homogeneous equation is the same with equals 0 on the right hand side. And this again is, well, the auxiliary equation is r squared plus 2r plus 1 equals 0, which is r plus 1 squared. So our basis for the solution space of H is e to the negative x and x e to the negative x. Now for our particular solution, we would have guessed y equals a naught e to the negative x. But since negative 1 is a root of the auxiliary equation of multiplicity 2, we multiply this guess by x squared. So yp equals a naught x squared e to the negative x. Then the derivative is, let's see, derivative of the first, 2a naught x times the second, e to the negative x, plus derivative of the second, negative e to the negative x times the first, a naught x squared. So we've got 2a naught x e to the negative x minus a naught x squared e to the negative x. And the second derivative is, actually let's factor out an e to the negative x to make the second derivative easier to compute. So this is e to the negative x times 2a naught x minus a naught x squared. Actually, I guess we can factor an a naught out also. So a naught e to the negative x times 2x minus x squared. So the second derivative is derivative of the first minus a naught e to the negative x times the second, 2x minus x squared, plus derivative of the second, 2 minus 2x times the first, a naught e to the negative x. And if we collect terms, we have, let's see, constant times e to the negative x is going to happen only over here. Actually, I'll keep a naught and e to the negative x outside, and then we have negative 2x plus x squared minus 2x minus 2 more x plus 2. So a naught e to the negative x squared minus 4x plus 2. Alright, now if we compare, if we plug this in to NH and set that equal to e to the negative x, we should be able to solve for the coefficient a naught. So plugging into NH, we have, let's see, y double prime. We're going to want to compare coefficients of x on both sides of the equation too. So plugging into NH and comparing coefficients of, guess we have e to the negative x, x, e to the negative x, and x squared e to the negative x on both sides. We have, oh, I erased yp, so yp equals a naught x squared e to the negative x. All right, we have on the left-hand side, so yp plus 2 times the derivative plus a second derivative. So we have that plus 2 times the derivative, which is right here. Plus the second derivative, which is right here. And on the right-hand side, so I guess I can get rid of all of this. We have e to the negative x plus 0 x e to the negative x plus 0 x squared e to the negative x. So coefficients of the same functions have to be equal. Let's see, so the coefficient of x squared e to the negative x on the left is, on the left-hand side we have a naught minus 2a naught plus a naught. And on the right-hand side, 0. All right, so this just says 0 equals 0. That's not much information. Coefficients of x on both sides. On the left-hand side, well, x e to the x really. So 2x times 2a naught. So that's 4a naught. And here's another x, minus 4a naught. And x e to the x, we don't have that on the other side. And if we compare constant terms, none there, none there. Oh, here's no x. So 2a naught. And on the right-hand side, no x times e to the negative x. So that equals 1. So I guess a naught equals 1/2. So that means that our particular solution is I might have, this is it right here. So is 1/2 x squared e to the negative x. And then all solutions are 1/2 x squared e to the negative x plus all multiples of e to the negative x plus all multiples of x e to the negative x. All right, now here's sort of a tricky example. Let's look at the non-homogeneous equation y double prime minus 2y prime equals 12x. So there's no y in it, just y prime and y double prime. Then the homogeneous equation is y double prime minus 2y prime equals 0. The auxiliary equation is r squared minus 2r equals 0. And that factors as r times r minus 2. So the roots are 0 and 2. Now the right-hand side of the non-homogeneous equation is 12x, which I'm going to write as 12x e to the 0x, because it's 12x times 1 and e to the 0x is 1. Now 0 appears as a root in the auxiliary equation. So that means that we have to multiply by an extra x when we... So we might guess yp equals a naught plus a1x because of the form of 12x, but we actually have to multiply by an extra x in there because 0 is a root of the auxiliary equation, and this is technically equal to 12x times e to the 0x. So we're going to use yp equals x to the 1 a naught plus a1x, which is a naught x plus a1x squared instead. And again, this x to the 1 equals the multiplicity of 0 as a root of the auxiliary equation. So yp equals a naught x plus a1x squared. Yp prime equals a naught plus 2a1x, and yp double prime equals 2a1. So y double prime minus y prime, yp double prime minus yp prime, is 2a1 minus a naught plus 2a1x, and that's supposed to be equal to 12x. So 2a1 minus a naught minus 2a1x, and this is 12x. So minus 2a1x equals 12x. So that means that a1 equals negative 6 if we divide both sides by negative 2. And then if we look at constant terms on both sides here, this is 12x plus constant term of 0. On the left-hand side, we've got 2a1 minus a naught. 2a1 minus a naught equals 0. a1 is negative 6, so this is negative 12 plus a naught, negative 12 minus a naught equals 0. So negative 12 equals a naught, if we put that on the other side. Okay, so here we have a naught and an a1. So yp equals negative 12x, and a1 is negative 6, minus 6x squared. And then all solutions are negative 12x minus 6x squared plus anything e to the 0x plus anything x. Oops, sorry, anything e to the 2x. E to the 0x is just 1, so I can say any constant. This comes from the homogeneous equation, and this is our particular solution. Darn it, I just found a typo. I wasn't supposed to subtract second derivative minus 1 times first derivative, but second derivative minus 2 times first derivative. So this should really have a 2 in here. And that should have a 2. So we've got 2a1 minus 2a0. And then minus 4a1x. And that should be equal to 12x plus 0. So if we look at coefficients of x, we have minus 4 here instead of minus 2. Minus 4a1x equals 12x, so a1 is minus 3. And then if we look at constant terms, we've got 2a1 minus 2a0 equals 0, which means that a1 and a0 are the same as negative 3. So our particular solution doesn't have these coefficients negative 12 and negative 6, but negative 3 and negative 3. And then all solutions are minus 3x squared, plus all solutions of the homogeneous system, the homogeneous equation. All right, finally I'd like to do one example where we have a right-hand side that's got a polynomial part and an exponential part. So y prime minus 3y equals x e to the 3x. This is a first order differential equation because all we see is the first derivative. The homogeneous differential equation is y prime minus 3y equals 0. The auxiliary equation is r minus 3 equals 0. So a basis of the homogeneous solution space, which is one-dimensional, is just e to the 3x. Alright, so now we've got two complications. We're multiplying e to the 3x by x here, and we need to multiply by an extra x to compensate for the fact that 3 e to the 3x already appears as a solution of the homogeneous equation. So we would guess yp equals a0 plus a1x e to the 3x just by the form here. We've got a first degree polynomial, so we have our general first degree part here. But instead, we're going to guess yp equals x to the first because of this multiplicity 1 occurrence of 3 as a root of the auxiliary equation, x to the first a0 plus a1x e to the 3x. So that makes yp equal to a0x plus a1x squared e to the 3x. Alright, now if we take the first derivative and plug y and its first derivative in there, we get, let's see, derivative of the first, a0 plus 2a1x times the second, e to the 3x, plus derivative of the second, 3e to the 3x times the first, a naught x plus a1x squared so this is e to the 3x times a naught plus 2a1x plus 3a naught x plus 3a1x squared. Alright, now yp prime minus yp equals e to the 3x times a naught plus 2a1 plus 3a naught x minus a naught x plus 3a1x squared minus a1x squared. Oh darn it, we're doing minus 3yp. Let me start this over again. Yp prime minus 3yp equals e to the 3x. Let's do constant terms first. A naught, there's no constant term there, plus coefficients of x. 2a1 plus 3a naught x minus 3a naught x minus 3 because we're taking away 3 of this plus 3a1x squared minus 3a1x squared. So these two are going to cancel each other. And that is e to the 3x times a naught plus 2a1 plus 3a naught minus 3a naught x. Okay, so those two cancel each other. And we just have 2a1x. Now this should be equal to the right-hand side, which is x e to the 3x. So that means what's inside here is x. So a1 has to be 1/2. And a naught has to be 0, because this is x e to the 3x plus 0 e to the 3x without an x. So comparing the coefficients of x e to the 3x and just regular e to the 3x on both sides, we get 2a1 equals 1 and a naught equals 0. So a1 equals 1/2, a naught equals 0, and yp is a naught is 0, so we just need the x squared part. 1/2 x squared e to the 3x. Then all solutions, of course, are going to be this particular solution, 1/2 x squared e to the 3x plus any multiple of e to the 3x, because that comes from the basis of the homogeneous solution space. All right, 5 examples is a lot for one video, so the end.